Welcome to this lesson on variance and standard deviation. In biostatistics, simply knowing the average of a dataset is rarely enough to understand the full picture. Today, we're going to explore how to measure the spread, scatter, and consistency of data. By the end of this video, you will understand not just how to calculate these essential metrics, but exactly what they mean in real-world biological and medical scenarios. Let us dive in. To begin, let us imagine you are comparing two archers competing in a tournament. Both archers have an average score of exactly 8 points per shot. However, the first archer consistently hits the 8-point ring every single time, while the second archer wildly hits 10s, 6s, and sometimes even misses the target completely. If you only look at their average score, they seem identical, but their consistency is completely different. This is exactly why we need a way to measure the spread or scatter of data, not just the center. We need tools that tell us how spread out our numbers are from the average. Now that we understand why measuring spread is important, let us define our first tool, variance. In biostatistics, variance is formally defined as the average of the squared differences between each individual data point and the mean of the dataset. It quantifies the degree of dispersion, or scatter, in a set of observations. You might wonder why we square the differences. Because variance squares these values, it treats negative and positive deviations equally, ensuring they do not just cancel each other out. Furthermore, squaring heavily penalizes extreme outliers, giving us a very clear mathematical picture of how scattered the data truly is. While variance is mathematically highly useful, it introduces a significant practical issue. Because variance squares the differences, it also changes the units of measurement to units squared. For example, if you are measuring plant height in centimeters, your variance will be in square centimeters, which can be hard to interpret. To fix this unit problem, we use the standard deviation, which is simply the square root of the variance. The standard deviation brings our measurement of spread back into the exact same units as our original data, making it much easier to understand, visualize, and communicate to others. Understanding this spread of data is absolutely critical in the biological and medical sciences. Imagine a new blood pressure medication that lowers blood pressure by an average of 20 points. If the standard deviation is very small, it means almost every patient experiences a safe, predictable 20-point drop. However, if the standard deviation is very large, the drug might dangerously drop one patient's pressure by 50 points while doing absolutely nothing for another patient. Without measuring variance and standard deviation, doctors would never know if a treatment is consistently safe or wildly unpredictable. Before we look at the mathematical formulas, we need to understand a crucial distinction in statistics. Statisticians use slightly different equations depending on whether we are measuring an entire population or just a small sample. A population includes every single individual we care about, while a sample is just a smaller group selected from that population. In biostatistics, we almost never have access to an entire population, so we rely on samples. Because samples are smaller and might miss extreme highs and lows, they require a slight mathematical adjustment to ensure our estimates of spread are accurate. Now that we know the difference between populations and samples, let us first look at the formula for the variance of an entire population. Conceptually, this formula calculates the exact average of all squared deviations from the center. The symbol sigma squared represents the population variance. The Greek letter sigma tells us to add up a series of values. The variable x sub I represents each individual data point, while the Greek letter mu represents the population mean. We subtract the mean from each data point, square that difference, add them all together, and finally divide by capital N, which is the total number of items in the population. If data points move further from the mean, the variance increases significantly. Since we usually work with samples, we must adjust our previous formula. This brings us to the sample variance formula, which includes a special mathematical adjustment called Bessel's correction. Here, the symbol s squared represents the sample variance, and x bar represents the sample mean. The most important change is in the denominator, where we divide by n-1 instead of just n, with n being the total number of observations in our sample. Dividing by a slightly smaller number makes the resulting variance slightly larger. This perfectly corrects for the fact that a small sample tends to underestimate the true spread of the full population. As the sample size n increases, this correction becomes less noticeable. Having calculated the sample variance, we can now find the standard deviation. Conceptually, this step reverses the squaring process that happened earlier in the numerator. In this final equation, S represents the sample standard deviation. We simply take the square root of the sample variance, S squared. This ensures that if our original data was measured in kilograms, our standard deviation is also measured in kilograms, rather than kilograms squared. It is the most common way scientists report the spread of their data in research papers. If the data points move closer to the mean, the value of S will decrease, indicating a tighter, more consistent dataset. Before we move on, let us see this with a concrete example. Suppose a botanist measures the heights of 5 rare plants, giving us values of 10, 12, 14, 15, and 19 centimeters. We need to find the sample standard deviation. First, we calculate the sample mean by adding all heights and dividing by 5, which gives us 14 centimeters. Next, we find how far each plant deviates from this average and square those differences to ensure they are positive. Adding these squared values gives us a total sum of 46. We then divide by n-1, which is 4, to get a sample variance of 11.5 square centimeters. Finally, taking the square root gives us our answer. The individual plant heights deviate from the mean by about 3.39 centimeters on average. Now that we have used this formula for plants, let us look at a clinical example involving patient heart rates. A cardiologist tests a pacemaker on 4 patients, recording resting heart rates of 72, 76, 72, and 80 beats per minute. We want to ensure the pacemaker keeps heart rate stable. We start by finding the mean, which is 75 beats per minute. We subtract this mean from each patient's heart rate, square the results, and add them together to get a total squared spread of 44. Since we have 4 patients, we divide by 3 to apply Bessel's correction, giving a variance of 14.67. Taking the square root yields our final standard deviation. The heart rates fluctuate by about 3.83 beats per minute, indicating the pacemaker is keeping the rates quite stable. Having calculated these values, let us visualize what standard deviation actually looks like. On this graph, the horizontal axis represents our data values, and the vertical axis represents how frequently those values occur. Both curves are centered on the exact same mean, represented by the dashed vertical line. The tall, narrow blue curve represents a dataset with a small standard deviation. Notice how tightly packed the data is around the center. In contrast, the short, wide red curve represents a dataset with a large standard deviation, The data is spread much further out into the tails. This diagram perfectly illustrates why the mean alone is not enough. The standard deviation tells us the true shape and reliability of our data. To wrap up our lesson, let us review the key takeaways. We have learned that variance is an essential tool that gives us the average of the squared deviations from the center of our data. However, because variance squares the units, the standard deviation is much more practical as it returns the measurement to its original intuitive units. We also saw that when working with samples, we must use Bessel's correction, dividing by n-1 to get an accurate estimate. By mastering these concepts, you can now look past simple averages and truly understand the reliability, consistency, and hidden variations within any biological dataset. Great job following along.